A SCADA system is described by three element types: Remote Terminal Unit, RTU, Master Terminal Unit, MTU, and their communications. A remote terminal unit is a multi-purpose device used for remote monitoring and control of several devices and systems used in the automation industry. Signals to the remote terminal unit from the MTU are discrete control orders, analog setting instructions, stepping motor pulses, and orders to respond. Signals from field devices are 4 to 20 milliamp field analog signals, 0 or 24 volt alarm switch signals, 0 or 24 volt equipment status signals, pulse train meter signals, and RS-232 serial messages from field equipment. Signals from the remote terminal unit to the MTU are field analog signals, alarms, equipment status, totalized meter signals, and equipment messages. Signals to field devices are contact closures or 0 or 24 volt control, 4 to 20 milliamp analog control, pulse train stepping motor control, and RS-232 serial messages to field equipment. The description of an RTU can be expanded into boxes. Communications interface allows the user to send and receive data to or from the MTU through a modem. A CPU, which contains program memory, configuration memory, and field data memory. And field interface allows the user to send and receive data to or from the field through output conditioners or input conditioners. While an RTU is in receive mode, part of the communications interface equipment receives a serial signal from the communications medium. This signal is converted to a stream of bits that are either ones or zeros. The fields of a binary message are the message establishment, information or data, and the message termination. The message establishment field has two subfields, sync and remote address. The sync subfield establishes that an MTU is sending a message to an RTU, and it also synchronizes the RTU clock to the MTU clock. The remote address subfield defines which RTU the message is being sent. The information or data field has several subfields: function, internal address, modifier, special features, and data. The function subfield defines the type of response that the RTU must make to this message, or the type of control message that the MTU is now transmitting. The internal address subfield identifies the location within the RTU. The modifier subfield defines the number of data units to be transferred. The special featured subfield allows for special instructions to the RTU, and the data subfield provides for generalized data to be sent from the MTU to the RTU. The message termination field consists of one subfield, the security code. The security code subfield is calculated at the MTU based on the information sent by the MTU. The RTU reads the information that is received and uses the same algorithm to calculate a 16-bit security code. When the entire message is received and confirmed as correct, the RTU will perform the instructions contained in the message just received. The RTU will refer to its memory registers, pull out the appropriate information, develop a message to the MTU according to similar rules and using the same protocol, and tell the MTU what those registers contain. Some of the messages from the MTU relate to control. They require the RTU to develop and transfer a signal to one of the field devices near its location. These control methods contain discrete control, analog control, pulse control, and serial control. For discrete control, the RTU will locate the registers that are allocated to controlling discrete outputs. Notice that since each register is 1 octet or 8 bits long, and each bit is able to define closed, positioned by 0, and open, positioned by 1, each register can control 8 discrete elements. The RTU will locate the first specified register position, position 32, and register 4, and will force it to a 1 state. It will then move to the second position, 33, and will force it to a 1 state. A couple of milliseconds later, the register is routinely read. At this point, because these two registers have a 1 in their specified positions, the RTU will cause 2 control relay drivers on an output card to latch 2 relays closed. Notice that the latching, either at the relay driver or the relay itself, causes the effect to be fell to last position. The output control relays will be used to energize solenoids to field devices. For analog control, it is very similar to discrete control as to 1s and 0s are placed into a certain register containing 8 bits. A couple of milliseconds later, this register is routinely read, and these values are compared to a clock pulse and moved to a buffer register. In an analog output card, these bits must be reconstructed into an analog signal. The first bit, called bit 0, is the most significant bit. Because it has a 1, it turns on a voltage source that outputs 5 volts. The second bit, because it is also a 1, turns on a voltage source of 2.5 volts. All of these voltages are added, and the resulting 7.5 volts is fed to a power driver and amplified to field devices. From here, it may be turned into a 4 to 20 milliamp signal. In fact, the signal would be more likely to act as a remote set point of a PID controller. Suppose the MTU instructed the RTU to open a valve, not all the way, but only to 75% of fully open. This would be handled by an analog control instruction. The MTU message will call for an analog output, register number 22 in this example, and set it at 75. In this case, it takes more than 1 bit to define the requirement, and register 22 has 8 bits. However, more data is required to define the degree of openness of the valve. 8 bits will allow 1 part in 2 to the 8th power, or 1 in 256, which is about 0.5%. For many control applications, including this one, 0.5% is all that we need, so 8 bits of precision is adequate. Applications that need more precise control use part or all of a second 8-bit register. 16 bits results in a precision of 1 in 2 to the 16th power, or 1 in 65,536. For this example, 8 bits of the 22nd analog register have been set to 11000000, which is 75% of 256. Many end devices, such as sensors and actuators, are equipped with serial output and input capability. This capability simplifies the movement of data between instruments and RTU registers. One of the most common data acquisition functions that a SCADA system can be called upon to perform is the monitoring of discrete status or alarm points. These are sometimes called digital points. In this example, a high-level switch on a hydroelectric reservoir The wiper side of the switch, LSH101, is supplied with 24 volts DC from the RTU. When the water level gets high enough to open the switch, the voltage on the return wire will change from 24 volts DC to 0 volts DC. This new voltage will be recognized by a signal conditioning circuit in the RTU. Here, transients, AC noise, and the effects of switch contact bounce are removed, and the electronics transfers the conditioned signal, in this case a 5 volt level, into discrete input register number 20, bit 7 as a 1. The next time the MTU asks the RTU for the status of discrete input register 20, bit 7, the RTU will look at this bit and report that is a 1. The MTU will then know that the water level in the reservoir is high. In this example for monitoring analog signals, there are two parts, at field and at the RTU. At the field, a level transmitter is used to transmit the level of a fluid in a reservoir. The level transmitter is in series with 24 volts DC, implementing a 4 to 20 milliamp signal. At the RTU, a signal converter contains sample, hold, transient suppression, and a low-pass filter to remove any noise in the signal. The 4 to 20 milliamp signal is then converted into a digital signal. The digital signal is then converted to a routine clock pulse and moved to a buffer register. Many sensors or local instruments that originally output their information via odometer-style readouts have been modified to be read by SCADA. Often, the least expensive way is to have the device send a string of pulses or interrupt a current from the RTU by opening and closing a relay contact in such a way that each open-close cycle represents a fixed known amount. In this way, the RTU can count or accumulate these contact closures and infer from their sum how much the device has measured. A totalizer may be external or internal to the RTU. Here, an external totalizer outputs a contact closure for each barrel of oil that passes through a turbine meter. This contact closure is energized by the 24 volt DC supply from the RTU, and the intermittent signal is fed into a signal conditioner. The output from the signal conditioner is then passed into a counting circuit that is composed of flip-flops and steering logic. Typically, the counter will have 16 bits and so can count up to 2 to the 16th power, 65,536 engineering units. Like most analog and pulse count inputs, a serial signal is sent to the RTU from an electronic processor of some kind. This will very often be a complex device such as an engine vibration analyzer or a process stream chromatograph. Usually, the signal or signals can be presented in the form of analog signals, but because the signals exist within the electronic processor as digital signals, it is easier to move them as serial digital signals. The physical connection used is often a RS-232 link. Acting as a master, the RTU signals the field device to respond. The device identifies itself and sends a serial message with a very fixed format, essentially telling the RTU all it knows. The RTU stores its data in registers as it comes in. When the MTU scans the RTU includes this information with everything else it sends. A simple SCADA system consists of an MTU with communication to or from the operator, and an RTU with communication to or from field devices. Somehow, the MTU and the RTU must be equipped to communicate with each other. The MTU and the RTU are each called Data Terminal Equipment, DTE. They each have the ability to formulate a signal that contains the information they must be sent. They also have the ability to decipher a received signal to extract its information. What they lack is the capacity to interface with the medium. The modems, which can be called Data Communication Equipment, DCE, are able to receive information from the DTEs, make the necessary changes to the form of the information, and send it over the medium to other DCEs, which will receive it and transfer it before passing it to another DTE. A protocol is a set of rules that defines the meaning of a pattern of binary words. A protocol supplies the code to create this long series of ones and zeros. The same code, or protocol, allows the receiving station to decode it. Although there are several protocols to be used, it is important that SCADA developers ensure that the same protocol is used for all stations that will communicate with each other. This figure shows the communication of two systems using the same protocol. The OSI model consists of 7 layers. Layer 7 is the application layer, Layer 6 is the presentation layer, Layer 5 is the session layer, Layer 4 is the transport layer, Layer 3 is the network layer, Layer 2 is the data link layer, and Layer 1 is the physical layer. Synchronous and asynchronous refer to the need for a timing signal to be transmitted with the data. Synchronous modems must transmit a clock pulse that is used to ensure that the receiver is working at the same clock speed as the transmitter. Asynchronous modems do not require that the receiver be clock synchronized with the transmitter. Start a message and end a message signals are required to advise the asynchronous receiver of the status of a message. Communication can be a one-way pass of information or a two-way exchange. Simplex systems allow information to be passed in one direction. Full duplex communication allows information to be transmitted and received at the same time. Although, since SCADA systems require two-way movement of information, it does not use simplex communication.